Hi everyone, my name is Vaishnavi Nalavan. Today I will be presenting on waste heat recovery from a diesel generator using a Rankine cycle. Diesel generator sets are commonly used in remote and rural areas for electricity supply. However, they operate with a low efficiency and consume large amount of fuel which leads to high operating costs and environmental issues. Typically, only 30 to 40 percentage of fuel energy is converted into useful power, while the rest is lost as exhaust heat. The Rankine cycle based waste heat recovery system captures these exhaust heat and converts it into additional electrical power and fresh water as shown in the system diagram. Based on the literature review, this study addressed three main problems. First, there is significant energy waste due to exhaust heat losses. Second, many remote and island regions face limited electricity supply and freshwater scarcity. Third, conventional diesel generator systems do not integrate waste heat recovery efficiently. Therefore, the objectives of this project are to analyze the operating principles of the Rankine cycle-based waste heat recovery system applied to a 1.1 megawatt diesel generator set, optimize additional power and freshwater production, evaluate key performance parameters, and assess the economic feasibilities of the system.
Good day. My name is Arunavi Anapumban Asogar and my matrix number is 241110912. And today I'll be explaining on literature review of waste heat recovery system. So first of all, what is waste heat recovery? Waste heat recovery is a method to capture unused heat from sources like engine exhaust and convert it into this is important because a lot of energy is normally wasted as heat. My review focuses on studies that use waste heat recovery for power generation and in some cases combined with water production. So the aim is to understand the systems used, their performance, and the main challenges reported in recent research. So, for the key findings from the literature, most studies use the Rankine cycle and especially the organic Rankine cycle, and also we can call it as ORC. ORC is preferred because it works well with low to medium temperature waste heat. Many researchers reported that these systems can significantly improve overall efficiency. By using exhaust heat, electricity can be generated without extra fuel. Some works also combine power generation with water production, which makes the system more useful. Overall, the results show that waste heat recovery has strong potential in real application. From the literature review, several key findings support our project analysis. Heat exchange studies highlight the importance of effectiveness, Nusselt number correlations, and pressure drop characteristics in validating thermodynamic models. Research on seawater based systems shows that corrosion and fouling are major challenges, making proper material selection and maintenance essential for long term reliability. Comparing existing waste heat recovery studies also reveals differences in cycle configuration, power output, freshwater production, and efficiency, which helps position our case study within the broader research context. That's all from me. Thank you so much.
Hello everyone, my name is Lim Yishen and this presentation explains the methodology section of my individual report on the waste heat recovery system. My role focused on understanding the thermodynamic modeling and the optimization approach. I will briefly explain the system configuration modeling software and optimization method. Okay, point to the figure. The system recovers exhaust heat from a 1.1 megawatt diesel generator using an open Rankine cycle. Seawater with the 3.5% salinity is used as the working fluid to produce the extra power and fresh water, improving the overall efficiency. The system is modeled using the engineering equation solver EES. EES is suitable because it solves the mass and energy balance equation, has the thermodynamic property database, support the optimization under the constraint. We can refer the EES website and the diagram in the slide. Point to figure in the slide. Three shell and tube heat exchangers are used. Economizer preheats seawater. A boiler to generate the steam, and a superheater to raise the steam temperature to 362.5 degrees Celsius. And then next, the key constraint includes the minimum 20 Kelvin pinch point and exhaust back pressure above the 100 kilopascal, turbine pressure from 40 bar to the zero point 0.3 bar. The system is optimized to maximize the power output while minimizing cost and weight. A multi-objective genetic algorithm NSGA2 is used to find the best trade-off by the adjusting number of tubes, tube size, and exhaust gas conditions. In this slide, the main assumptions include steady-state operation, constant seawater properties, and fixed turbine and pump efficiency. For the key challenge are corrosion due to seawater, system integration, and the control under the variable exhaust conditions. So, in the conclusion, this methodology explains how the WHR system is modeled and optimized using the EES. It provides a clear framework for improving the energy efficiency in diesel generator system. Thank you.
I'm Li Mingshen. Now I'm going to discuss about the results and analysis. This is the flow diagram for diesel engine which using the Rankine cycle. The Rankine cycle is used because it's suitable for medium to high temperature, which is exactly what diesel exhaust provides. This is the TS diagram shows the thermodynamic heart of our waste heat recovery system. Starting at 31 degrees Celsius, seawater is pumped to high pressure. It's heated to 250.4 degrees Celsius where it boils, then superheated to 362.5 degrees Celsius, ensuring dry steam for turbine protection. The steam expands through the turbine, generating 131 kilowatt of electricity, then condenses at 69 degrees Celsius, producing fresh water. This optimized cycle shapes maximize work output while meeting all design constraints. This is the overall system performance. Our optimized system achieves additional power output 131 kilowatts. That's enough extra electricity to power approximate 13 average Malaysian households. Freshwater production is 8.56 million liters per year. This meets the daily water needs of about 65 people. For efficiency improvement, 11.75 reductions in breakthrough consumption and 10.51 increase in overall system efficiency. This number tells us that we are not just recovering waste heat, we are significantly improving the entire system performance. For the superheater, which heats steam from saturations to 362.5 degrees Celsius, we tested five different tubes configurations. 217 and 271 tube designed failed because they couldn't maintain the required for 100 kilopascal exhaust pressure. 397 and 469 tube designed failed because they couldn't reach the target temperature of 362.5 degrees Celsius. 331 tubes was the Goldilocks choice, meeting all constraints with the lowest weight of just 7.405 tons. Why couldn't design with more tubes reach the target temperature? Because more tubes mean lower fluid velocity, which reduced the heat transfer coefficients. Even with more surface area, they couldn't transfer heat effectively enough. For the economizer, which preheats incoming seawater, we select 817 tubes. This design weighs 7.495 tons, has an aspect ratio of 1.677, which is very compact, achieves a heat transfer coefficient of 17.82. Most importantly, maintains exhaust pressure above 100 kilopascal. The boiler, where seawater turns to steam, used 919 tubes, weight 9.327 tons, heat transfer coefficients 19.46. These were chosen over lighter options because 721 and the 817 tube design couldn't meet the 100 kilopascal pressure constraint. For trade-off 1, tube count versus pressure. More tubes means that lower tube side pressure drop, but more tubes means higher shell side pressure drop. We balance this to keep total pressure acceptable. For trade-off 2, heat transfer versus size or weight. Designs that maximize heat transfer become impractically large and heavy. We found that sweet spot where performance meets practically. For trade-off 3, thermal versus economic performance. The lightest designs were thermodynamically infeasible. The best thermal performance were economically prohibitive. We selected cost-effective designs that meet all technical requirements. This is the first principle analysis, where heat transfer depends on the overall coefficients, surface area and temperature difference, and they must maintain exhaust pressures more than or equal to 100 kilopascal and pinch temperature more than or equal to 20 Kelvin.
My name is Siti Nohrani binti Muhammad Azali. In this slide, I will show how we replicate the waste heat recover system model using engineering equation solver. The goal is to check the system performance like power output, efficiency, and payback period. First, we set the key parameter like mass flow rate, turbine pressure, and exhaust gas temperature, which are needed for the Rankine cycle. Finally, we calculate the system efficiency and payback period by dividing the capital cost by the annual revenue from electricity and water production. This process helps us understand how well the system works and how long it takes to recover the investment. This slide shows the cost of waste heat recovery system. The total capital cost is 734,700 USD, which an annually maintenance cost of 30572 USD. The system can produce 8.56 million liters of fresh water each year. In terms of payback period, electricity only production take 4.8 years. Freshwater only take 4.63 years, and combined electricity and freshwater production has the shortest payback period of 2 years, making it the most efficient option. This slide shows how exhaust gas temperature and turbine pressure affect the performance of the waste heat recovery system. Higher exhaust temperature and higher turbine pressure make the system work better. This increase power and water production, raise revenue, and help recover the cost faster. This graph compare the efficiency of water R245FA and R141B at different temperature. As temperature increase, efficiency also increase for all fluid. R245FA perform the best, especially at low temperature, and R141B perform better than water and work well at medium temperature. This slide shows the localized economic analysis of the wet heat recovery system in Malaysia. The model is adjusted to reflect local electricity price, water cost and fuel price. The capital cost is RM 3.38 million. Electricity price is RM 0.874 kilowatt per hour with an 5% interest rate. This local factor help us assess the economic feasibility of implementing the wet heat recovery system in Malaysia.